All right, guys. So now that the introductions are out of the way, I have a little bit of information as to the kinds of people who come and take these Encompass trainings. So first, I want to say that furthering your education, even though you already have a job, is something we're not taught in school, right? So in high school, we're taught go to school, get your job, and then move on with your life. In the trades, it's different. We can't just go to college and be done with it because the trades are constantly changing. We have so much new technology. We have so many new things that we need to learn. And especially in maintenance, you guys aren't in one field. It is so hard to get all the information that you need. Luckily, Encompass is here to give you that. So I am going to do my part to give you guys bits and pieces of the HVAC trade as best I can. And if you want more HVAC training, you can go to skillcat.app or you can download the app in the App Store. So what I want to talk about today is the very fundamentals of HVAC. And a lot of you guys are in warmer climates. I happen to be in Maine, so I'm in the north. I have a lot more involved in the HVAC circuit here. A lot of you people who have 4 seasons in your states will too. But for today, because we only have about 45 minutes for this training, I really want to start at the basics. And the basics of HVAC will always be the refrigeration cycle. So it's easy to go up to a system and to throw parts at it, right? It's easy to say, this isn't working, we're going to change this part and hope it works. And we do that because we don't know what's happening within that contained system. And when things are out of sight, they tend to be out of mind. So what I'm going to do for you today is I'm going to break that whole thought process apart and I'm going to show you what's inside. So when you guys walk up to an apartment building that has, 20 condensers outside, they're an AC condenser. And then that somewhere inside the building, there's another piece, the evaporator, whether it's a mini split head or it's an A coil. It could be lots of things. But for this purpose, we're going to learn about it as an evaporator because that encompasses all of those different types that you can see. The condensers are pretty much the same. So I'm going to teach you guys what it means to follow the refrigeration cycle, what it means to troubleshoot it, what tools we use, and then I'm going to also teach you guys exactly what it's doing. So I'm going to turn my camera real quick. These materials were provided to us by Craig Migliaccio, the AC service tech, and they're amazing. They really help me with virtual training. So I'm going to try to do it so you can see as best as you can. So what we have here is the basic refrigeration cycle. So this is the same no matter what HVAC system you're working on. If it's a refrigerant-based system, this is the same. It may look different. It may have different parts and pieces to it, which I'm going to show you later. But this is the general refrigeration cycle. And it is a big, giant loop. And it just constantly does the same thing over and over again to achieve the temperature that we're looking for. So I'm going to teach you guys this in the way that it's cooling. There are obviously, we're seeing a huge increase in heat pumps. We're seeing all kinds of different heat pumps, things that can cool and heat. That is the majority of our lives in HVAC, especially in residential. But for this purpose, I'm going to show you it in cooling. Just know that if you're heating, the process is reversed. And I'll show you guys how that's done as well at the end of this. So there are 4 main components in the refrigeration cycle. We have the compressor, which is in the outdoor condenser. We have the condenser coil, which is also in the condenser. We have, these are your service valves that you hook up to with your gauges. We'll talk about that in a little bit. And then this is a filter dryer. This won't always be in this position, but it's here to show you just what it does. And then you have a metering device. You guys won't always see this style metering device. This metering device is what we call a fixed orifice metering device. A lot of the time you'll see a TXV or you'll see an EEV, and I will talk about those as well. But they all do the same thing. They all meter the refrigerant. And then going forward from there, we have the evaporator coil, which is exact and opposite from the condenser coil. And then we have another service port on the opposite side. As you can see, we always have service ports, 1 on each side. Sometimes you'll only have 1 on one side, and that's okay. I will teach you guys how to use that to your advantage as well. And then we're back to the compressor here. So the 4 main components of the refrigeration cycle are the compressor, the condenser coil, the metering device, and the evaporator coil. Now, some argue, a lot of techs argue that there are 5 and that the 5th is the thermostat because you cannot make this do what it does without a temperature reading device. So just know that if somebody ever says 5, the 5th one is the thermostat. Okay, so what I'm going to show you guys now is what each one of these components does, and then the exact order in which it's done. So it's a circle again, so you can start anywhere in this cycle that you want in order to explain it or to understand it. For this purpose, I'm going to start at the compressor. So the compressor is arguably the most important and most expensive part of your AC. So the compressor is the centralized part, and that's why I start here, because everything leaves and comes back to the compressor. So from the compressor, we go through the condenser coil, through the metering device, back through the evaporator coil, and then back to the compressor. As you can see on both sides, so these, just to show you guys what kind of the key of this map is, these darker colors are liquid refrigerant. So if you see dark blue or you see bright red, those are liquid refrigerant. And this is meant to show you how it changes phase within each component. So from the compressor, we're leaving the compressor as a high pressure, high temperature vapor. That is the compressor's job. The compressor compresses the refrigerant so that it heats up and the pressure rises. Pressure and temperature are directly related. If you raise pressure, you raise temperature. So it's built specifically to add pressure to that refrigerant so that it will turn into a high pressure, high temperature vapor. So it leaves the compressor in that form. It comes through the condenser coil where it condenses. So now it's a high pressure, high temperature liquid. So we think of condensing, condensate, right? So when pressure is added to something at that extreme amount, it's going to condensate. So that's why we have a condenser coil, and that's why we call it that. So as it condenses, it's a high pressure, high temperature liquid. And then it's going to come to the metering device. As it goes through the metering device is the opposite job of the compressor. So this metering device is specifically built to lower the pressure and then spit out just the right amount of refrigerant on the other side so that your flow is going to your evaporator coil. And then where the condenser condenses, the evaporator evaporates. So you can think of it in forms of water, but the temperatures are so very different. Where water boils at 212 degrees, we are not getting that with refrigerant. There are some refrigerants that actually evaporate in negative degrees. Most refrigerants actually evaporate in negative degrees Fahrenheit. So because of that, the temperature of a room is almost always warm enough for it to evaporate, right? So if you have a 74-degree room and your refrigerant evaporates at negative 50 degrees, then your room, no matter what, is going to be enough load to evaporate. So as it evaporates, it blows out that conditioned air. So we have a cooler temperature coming off of this coil this way into your home. And then it turns into a low pressure, low temperature vapor, and then comes back to the compressor. So as you notice, it's always a vapor when it comes to the compressor, and then it's always leaving as a vapor as well. This compressor cannot see liquid refrigerant, it will break. So what happens is the liquid refrigerant gets into the compressor, it gets into the valves, it gets into the scrolls, depending on what kind of compressor it is, and then it causes acidity. It causes the copper plating we hear about within the compressor, and that will damage all of the mechanical moving parts of the compressor, and eventually you'll end up with compressor burnout. This happens typically, liquid floodback is what we call it, and that happens typically if there's either a really bad restriction on one side for a very long time, or if it is overcharged. And if you overcharge a system, you can cause liquid floodback immediately, or it can take time. So it's very, very important not to overcharge a system. So that's the compressor's job. It takes the low pressure, low temperature vapor and spits out a high pressure, high temperature vapor. Again, the job of the condenser coil is to condense into a liquid. It's still high temperature though, and then it's going to come through the metering device, which job is the opposite of the compressor, to lower that pressure. And that's going to spit out a low pressure, low temperature liquid, which is then going to turn into a low pressure, low temperature vapor. to come back to the compressor. So that's how we're going to leave that for right now. So basically what happens is we have disruptions in that cycle, in that flow cycle. So there are many, many reasons that an air conditioner breaks. For right now, we're talking about the refrigeration cycle alone. As a disclaimer, I want to let you guys know that we always do what we call a non-invasive system check first. We never assume that it's the refrigerant. There's a standard that we call ABC, which is airflow before charge. So you're always going to check the outside of the coil to make sure that it's not dirty. You're always going to make sure that your airflow, your supply air coming out of your evaporator is the correct temperature, and that your release air out of your condenser is warmer than what's coming out of the house. So we do not blow cold air into a room. That's not how we air condition. That's how it feels to us as human beings with nerves on our skin. That's how it feels. That is not, in fact, what we're doing with this cycle. This cycle, like I just talked about, is meant to take a very low boiling point refrigerant, and that refrigerant goes through the cycle. It takes heat from that room. It grabs that heat as it's evaporating and as it's condensing. So as it's evaporating, it's taking the heat, and then it's traveling that heat through the pipes back out to the condenser. As the condenser condenses, it rejects that heat outside. So we are not blowing cold air into a room to make it colder. We're removing the heat. And that is a concept that is tough for a lot of people who haven't taken courses like these, who haven't gone to school for this. But if you always remember that that's what we're doing and that we rely on evaporation and condensation to do that, you will always understand the refrigeration cycle. So as we raise pressure, as we lower pressure, as we raise temperature, as we lower temperature, we are always removing heat and then rejecting it to another space. That's why you'll always see the condenser outside. It's meant to reject it into a place where it's not going to make anybody uncomfortable. And then you'll always see the evaporator inside, because the evaporation is what's grabbing that heat to remove it from your space. So we do have cooler air blowing out of the evaporator than the temperature of the room typically. That is not how we are conditioning. That's just a product of conditioning, if that makes sense. Okay, so knowing that that's why we use refrigerants, knowing all of these things. The biggest thing to remember is that when something breaks in an air conditioner, probably 8 times out of 10, and that's not an exaggeration, it's not going to have to do with the refrigeration cycle. What we're taught in school, and that's why I love to get people who haven't gone to school for this, because it's a lot less to undo. But in school, we're taught gauges hooking up. We're taught how to read pressures, how to read the temperatures that are coming out of our gauges, that what our gauges are telling us, our manifolds. That's all out the window until we do a non-invasive system check. So I will talk about that as well, because I don't want you guys immediately saying, oh, Jen said to hook up to these units every single time. That's not necessary, and it does happen. But when it happens, we come up with an incorrect charge. So to talk about charge a little bit, our charge, when you hear charge when it comes to an AC system, what we're referring to is the amount of refrigerant within the system. So if our system calls for X amount of pounds of refrigerant and we have less than that, then we have a low charge, and low charge causes its own problems. If it has more than that, then we have overcharging. And when it's overcharged, it has a whole set of other problems. So if we have discounted airflow, and airflow is fine, we've changed filters, we've cleaned coils, we know that there is no underlying cause for lack of airflow. And then we have inspected visually. We've done a visual inspection on that system to check all of the components. We open the wiring compartment. We see that there's no chewed or melted or burnt wires or exposed wires that are arcing. We have made sure that the thermostat settings are all correct. We have checked every other part of the system. That's when we move to refrigerant charge. So if we are at a point, sorry, hold on, guys. I'm just trying to bring up a little thing here. So If we're at a point where we've gone through all of those things, none of those are the problem. Then we need to check the charge. To check the charge, we're going to use what you guys have seen probably more often than not is analog gauges. I do have some, I just don't have any here with me right now. So I'm going to show you digital gauges. This is the majority of what you're going to see nowadays. Those of you who have been in the trades for a long time will have seen the analog, which is basically a blue gauge and a red gauge hooked to hoses. This is a digital manifold. This happens to be the field piece one. It's just what I use. It's not, I don't have any ties to them whatsoever, but so let me see if I can, yeah. So this is what it will look like when you are hooked to a system. It will not have these temperatures or pressures, obviously. This is not hooked up, but this is what your gauge manifold will look like. So this manifold is meant to tell you what's happening within the system by taking your high side and your low side, hooking them to those service ports that I showed you on the diagram, which I'll show you again. And then as you do that, it's able to cycle through. You become, because of this manifold, you become part of the refrigeration cycle. So the hoses are not the only important part of this. When we check pressures, we also need to check temperatures. So a lot of the issues that we have in reading what's going on within the refrigeration cycle is that we don't know all of what's going on. So with gauges like these, we can get a more comprehensive view of what's happening. These are temperature clamps. These go on your high side line and your low side lines. And these tell us what our superheat is. This manifold will automatically calculate superheat and subcool, which we'll talk about. And then they also tell us what our temperature differentials and splits are. They tell us a lot of things, you guys, liquid and vapor saturation, which is the temperature at which we are boiling and boiling and condensing. They tell us so many things. They're great, but we don't always need them. These are what we are using now. You guys will see these. You may not know that they are the same exact thing as what you were seeing back, 10 years ago when you were seeing the analog gauges with the blue and red gauge. But these are also gauges. These are manifoldless gauges. They are wireless probes. These also go one on the high side, one on the low side, same ports that you use for your regular gauges. These will tell us the same exact things. These hook to for this purpose, it's JobLink, but they hook to an app on your phone. So you hook these up, these transmit to each other, and then Bluetooth back to your phone. They will show you exactly what the gauge set showed you, but on your phone screen, which makes it a lot more technically efficient, but also you're not losing as much refrigerant. As you can see, these don't have hoses. We don't need hoses anymore to check systems. And when we do hook up hoses, there's a part of that charge that we're losing within our hoses. Also, manifolds can leak. So you could be chasing a leak in the system that's actually in your gauges. So, you spent 5 hours chasing a leak that wasn't actually there, which is not a lot of fun. I've actually been there. So these are wireless probes. This kit comes with the probes. It comes with, again, the temperature clamps, which are super important, you guys. If you have gauges, make sure you get some form of temperature clamps. Almost every company makes them. It's a very easy thing to make your life a lot easier. So then you're not calculating those temperature differentials by yourself. Your app will actually do it for you. And then we have these. These are psychrometers, is what we call them. You guys have heard the term psychometrics. That's what we use for airflow curves. These are built to measure airflow. So you put one in the supply, one in the return. It will tell you where and what your static pressures are within your systems. Also, they do temperature. So there's that. So these are the tools that we use to check the refrigeration cycle. So when I say non-invasive system check, you guys now know what that means. That means that we're not gauging up. We're using our eyes, ears, nose even. You can smell a lot of problems that are happening within the system. And then when there is nothing left to be found without gauges, that's when we use gauges, either probes or manifolds. So when we finally gauge up, we need to know what we're seeing, right? So I'm going to turn you guys back to the diagram, and I'm going to show you what's happening for each of the things that you'll see on your manifold or on your JobLink app. So one of the things that we'll show you is the pressures of each side. So refrigerant goes yes, by pound, and it goes by, I mean, I guess you could measure it by gallon if you wanted to. We use PSI, which is pressure. So pounds of pressure, basically. So when I hook up my gauges to these two service ports, right, I'm going to then see on my manifold or on my app the pressures of the high side and of the low side. For this, there are so many refrigerants out there, you guys, and I could never cover them in this amount of time. So for all intents and purposes today, I'm going to talk about 410A and R22. R22 is actually a banned substance already. 410A is on its way as well as we switch to A2L refrigerants, which we'll talk about a little bit at the end. But the majority of the systems that you see, some of them still have R22 in them. That's 100% legal. You don't have to rip out every system when a refrigerant goes out and is, blacklisted, but we do have to think about replacing them if they get a leak, if they, you guys would learn about this in the EPA course if you do decide to take that. SkillCat does offer it. But these refrigerants are harmful to the environment, basically. So we started out with R12 and R11, which were CFCs, chlorofluorocarbons. We found out chlorine, one molecule of chlorine in the atmosphere actually eats and disposes of over 100,000 ozone molecules. So chlorine eats oxygen. Oxygen is 3 oxygen molecules. Ozone is 3 oxygen molecules. So for every 1 molecule of chlorine in our atmosphere, it was eating over 100,000 ozone molecules, which is what caused, you guys have heard about it a million times, I'm sure, the hole in the ozone. Not exactly a hole, but an opening in our ozone that protects us. So when the EPA found that out, they switched to HCFCs, which are hydrochlorofluorocarbons. We call them HCFCs for a reason. It's much easier to pronounce. Those have fluorine, and they also have chlorine in them still, just not as much. So then we found out that R22, HCFC R22, is also damaging to the ozone layer, but also has a high GWP rating. A GWP rating is a global warming potential rating. You want as close to 0 as you can get. The smallest GWP rating that there is CO2, which is already in our atmosphere, and that has a GWP of 1. So the closer you get to that, the better. So that's why if you guys have heard anything about HVAC, I'm sure you have as maintenance techs, but if you've heard anything about what's happening right now, we are switching completely over to A2Ls, which are 100% better for the environment. They're very low GWP. A lot of them are natural refrigerants. A lot of the ones that are coming out after the A2Ls are natural refrigerants as well. Okay, so knowing that, we're going to go with 410A, which is an HFC, also not harmful to the ozone, but harmful to it has a high global warming potential. So it raises the temperature of the atmosphere and it causes it's a greenhouse gas. It causes the greenhouse effect. So high carbon footprint, not good. So we do not use that anymore in new systems as of this year, but you will still see it all the time. It's the most prominent one that's in air conditioners today. So for 410A, we have our high side and our low side pressures. 410A runs far cry higher than R22 used to. So older techs who have been in this game for a long time have heard of R22, have used that maybe on gauges. When you see R22, a properly charged system on R22, you'll see much lower pressures than you will for 410A. And that's because it's a zeotropic blend and there are more than 1 refrigerant in it. And R22 is just 1 refrigerant. So you're going to see a high side under a normal circumstance. You're going to see a high side pressure usually of 300 to 400, and then you're going to see a low side of lower than that, usually in the 120s, 150s, somewhere in there, depending on how your system is built to work. So as you gauge up, you see your high side and your low side pressures. That is only one thing that's being shown on those gauges. The other things are far more important. There's a lot you can tell if your pressures are very low on both sides, or if one side is very, very high, one side is very, very low. You can tell, that you may have a restriction, or you may be low on refrigerant, or you may be overcharged. But it's a point of access. It's not a be all end all. So what we don't learn about a lot, and even in school, is the rest of those numbers that are on that screen. So what I'm going to teach you guys about now is a little bit about those other numbers. So the first one that I want to start with is saturation temperatures. Saturation is when something is mostly a vapor or it's mostly a liquid. So when we come to these coils, right, we need to get a temperature that tells us at what temperature is it mostly liquid here in the condenser coil. And then on the other side, where is it mostly gas? So what temperature is this spot at where we're changing almost entirely from liquid to gas? And then this temperature here where we're changing almost entirely from gas to liquid. So those are important. If we have a very, very high liquid or very, very low liquid saturation, we could have too much liquid in one side. If we have very, very low vapor saturation, we could have too much vapor on one side, meaning there's a liquid line restriction. So this metering device, you'll see a TXV sometimes, but all metering devices clog. Sometimes they go bad. And when they go bad, the number one thing that happens is a restriction in this part of the system. So as I said, it's a circle. We've got to be able to keep going around and around and around. And when we have something wrong with this spot right here, it stops that cycle. So you could end up with all of your liquid on this side and then very little vapor on this side or very little liquid, depending on where your restriction is. So when that happens, we have got to study this, figure out what we can do to change it. If the whole part needs to be replaced, replace it. And then that way, once it's new and it's replaced again, we're able to start that system back up again. Now, that's not the only reason that your saturation temperatures will be off. If you overcharge or undercharge, they will also be off, because what it's telling you is at what temperature is it mostly liquid, at what temperature is it mostly vapor. If that is not correct, not where you want it, then there is something wrong within the system. So again, you could do a non-invasive system check and get those temperatures. We're using those clamps that I showed you. I'll actually grab one real quick. We're using those clamps. We're putting them on the liquid side, on the vapor side, and then we're taking that temperature and the temperature difference between them. You can do that without gauging up to the system. You just put the temperature clamps on. You can also take that temperature with a thermistor attached to your meter, or with a temperature probe you could tape to it. There are lots and lots of ways to check this without gauging up to the system. But one way is to gauge up. Your gauges will always tell you that. So if you've got a normally working system, you want the liquid saturation to be somewhere, for 410A, to be somewhere over 100. You want it to be hot on that side. If you have a normally working system, your vapor saturation should be relatively low. Not too low. It should be somewhere between, I like to see 30 to 50. 40 is my bread and butter. That's my sweet spot. But there are lots of reasons that it wouldn't be dead on. So it is kind of a spectrum. And if it's working within that spectrum, we're not going to, these are not critically charged units. By critically charged, I mean it has to be the exact to the gram bit of refrigerant. These are relatively wing it and ding it charge systems. So you can dial it in using your gauges. You can dial it in knowing what your liquid and vapor saturations are, what your superheat and subcool are, but it's never going to be the same for every system. So going on to that. So this is what saturation is. Saturation temperature is the temperature at which it is mostly liquid or it is mostly vapor within the system. If those numbers are not correct, you either have an overcharge, undercharge, or restriction. So the next thing that I want to talk about is superheat and subcool. There are systems, like we talked about before, that only have one valve to gauge up to. When that's the case, you will go without either your superheat or your subcool. Usually subcool is what you have, sometimes not. But so if you're going without your superheat or your subcool, you can still tell based on one or the other. So your superheat and your subcool are nothing more than a calculation. And we used to have to do that by hand using pressure temperature charts. Now we don't have to because our manifolds do them or our job link does them. It's still a good thing to know. Maybe Encompass can do a little short to teach you guys how to calculate subcool and superheat. I'm not going to do that right now. But when you gauge up and you put your temperature clamps on, it will tell you your superheat and your subcool. For a 410A system, we really want to see around 10 for your superheat, and I like to see, I say my sweet spot for subcool is around 14. It's going to vary again, but if you have a 2 superheat and a 50 subcool, then you've got too much liquid in your system, right? And if you've got a 50 superheat and a 2 subcool, you've got not enough liquid in your system, not enough refrigerant in your system. So it's either because it's trapped behind something like this TXD, like this metering device, or it's just not there to begin with. So that is what we see on our gauges. That's what I really wanted to talk about, because if you guys do go that route, you go to, say you download SkillCat, or you go to Esco or your local trade school and you take your EPA course, you will learn about the chemistry fundamentals. You will learn about what we call the core. And the core is why we do what we do. Why are these self-contained systems? Why do we need to recover? We need to be very, very careful about how we are releasing refrigerant. We cannot release it into the atmosphere for any reason. It's a $10,000 fine, and it's actually the federal EPA that comes down on you. You would absolutely lose your license to practice HVAC if you loose refrigerant into the atmosphere. That is not to be said for some A2Ls and for all natural refrigerants. So if you see a CO2 system, which you will not see in regular HVAC right now, you will see that in refrigeration if you see it. But if you see like a CO2 system, you just literally don't need to recover that at all. You just loose it into the atmosphere because it's already present and it's 100% natural. It won't raise the GWP. But if you have a refrigerant like 410A or R22, especially R22, because it has that chlorine in it, it's a $10,000 fine, and you are literally destroying our atmosphere. Now, for a little history, that is what we used to do. When this first started and we first came out with the R12s, R11s, R22s, we did not know what we know now. And because we didn't know, because that hole in the ozone did not exist and we didn't even know it was possible to make one, because of that, we just loosed it all into the atmosphere. In doing so, we created a serious, serious raise in global warming. We created greenhouse gas effects, and we created a hole literally in our breathable ozone. So that's what helps us to create the oxygen that we need to breathe. That's what protects us from lots of harmful things from space. So now that we know, we have to do what's called recovering. So when a system, say we have to change the TXD, the metering device, we'll just use that for an example. If we have to change the metering device or any part within the system where we have to cut into the refrigerant piping. So when we do that, we have to be very, very careful that there is no refrigerant in the unit. Now, one option is you can pump down the refrigerant into the coil, and then you can close off the system. Another is that you can pump it down into the receiver if it has one, and then close off the system, and then you can do your work and then re-release it. More often than not, we have to do what's called recovery. So to recover, we use our gauges, or if you only have probes, this is really the only thing that I say you need gauges for, but if you only have probes, you can still recover. You're just going to hook your hose directly from the system to your recovery tank, and you're not going to have a manifold to do that with. So that is 100% okay. It's not a big deal. The thing that comes after that, though, you definitely don't want to use the manifold for. And we do it. We do vacuum through manifolds. It just takes more time. It causes more possible problems because there are more connections. And again, you could be chasing something that's within your manifold and not within the system at all. But for recovery, we're going to take our gauges, we're going to hook them to our recovery cylinder. We're going recovery machine, and then we're going to also hook the recovery machine back to a recovery cylinder. So a recovery cylinder is pretty much just a refrigerant jug that is empty. So you're going to use the compressor to pull that refrigerant, or the recovery machine, depending on how you're doing this. You can use the compressor to pump it down, or you can recover it. If we're recovering, we're going to pull that refrigerant out of the system entirely through our recovery machine. And then we're going to put it into the new canister. We're going to close that canister off, and then we have an empty system. We're going to then go ahead and do our work. We are not going to evacuate or vacuum at that point. We're going to change our TXD or our piston metering device or whatever we're changing, the filter dryer. Sometimes there is a filter dryer in this. We will talk about what those do in a second. But we're going to change whatever we're changing, and then we're going to make sure we have a tight system again. So a tight system, I don't mean that I did a really good job, and so I'm saying it's a tight system. I mean that I have finished my work. I have double and triple checked my work. I've made sure that I brazed. Brazing, you guys, I'm sure you've seen it. It's like welding, but for copper. We are taking silver solder, and this for 410A, you have to use a different type, which is why it's called brazing and not soldering. Soldering is for water pipes and low, you can do that with R22, low pressure refrigerants. But with 410A, which is what you'll see most often, you need to braze. So what we're going to do is we're going to take our torch, we're going to put the flame on the pipe, we're going to take that silver solder, melt it, and cause a seal. Once we have caused a seal and capped it, we are then going to pressure test our system. So you can use lots of things to pressure test. What I like to use is nitrogen. You're also going to be flowing that while you're brazing so that you don't end up with oxidation within the pipe. So if you try to braze that pipe, you cut the pipe and your system's empty and you braze that pipe without flowing nitrogen through your pipe, you're going to end up with debris from that. You're going to end up with oxidation, which is basically a form of rust. You're going to end up with all kinds of stuff within your system, and these systems need to be 100% clean, and I mean sterile clean, dry, no moisture, no debris, no nothing. So if you're flowing with nitrogen, you will end up with clean pipes inside and out. So once you're flowing nitrogen, you've done your brazing, you've fixed the system. Now you're going to purge with nitrogen. You're going to fill the system with nitrogen, and you're going to set that at whatever poundage that you want to test at. I like to test between 300 and 500 PSI. It's up to you, as long as it's enough. Once you are completely pressurized with nitrogen, you are going to just wait and watch. So 15 minutes later, 30 minutes later, roughly within there, you are not going to see a drop in your nitrogen pressure if there is not a leak. However, if there is a leak, you will lose that pressure from your nitrogen. If you have a drop in nitrogen from the time that you charged it with nitrogen to the time that your pressure test is over, then you need to go back to that connection or any connections that you did fix, and you need to inspect them, figure out why it is that it's leaking, or it could be a potential other leak in the system that you didn't see to begin with. So we're going to go back through, put a little bit of refrigerant in the system and do a leak sniffer test with a leak detector, or we're going to use bubbles, and we can use air or nitrogen for that on every connection, just to see if you use big blue bubbles from Refrigeration Technologies, for instance. You'll spray it on the connection. Bubbles will form if you have a leak. If you don't have a leak, no bubbles will form. So you're going to go back, and then you're going to have to do that again before you vacuum. If your pressure test is good, you're going to then loose your nitrogen, because again, nitrogen is not something that we have to regulate. It's already present in our atmosphere, 100% safe. You're going to loose your nitrogen into the atmosphere, and then you're going to begin the evacuation the evacuation part of what you're doing. So evacuation is sometimes called vacuum. Yes, what you are doing is vacuuming down the system. You're pulling the system into a vacuum. It doesn't mean that we're sucking all the air out of it, but essentially it does. So we're going to use a vacuum pump at that point with oil in it. That's going to remove all of the moisture and all of the, minuscule debris, anything like that that we have in the system. It's going to remove it as best it can. If you have a very wet system, or if you have a very debris-filled system because you didn't braze with nitrogen, you're going to have a harder time at pulling down that vacuum. So what we do is we hook our gauges at that point through the vacuum port. We hook it to our vacuum pump, and then the vacuum pump to the system. The vacuum pump is then going to pull and pull and pull and pull, and it's going to gurgle through the oil. So what it does is it essentially pulls all that moisture and whatever out of the system. It brings it through the oil to basically dispose of it. So as we're pulling, we're going to be watching what's called our microns. The gauges that I have shown you, and the gauges that I have shown you do have a built-in micrometer. We do not like to use that. We like to use a separate micrometer. You want to be able to know for a fact that the microns that you're reading are correct. So as we pull vacuum, the ideal system pulls down under 500 microns. And then as we shut off our vacuum pump and isolate our gauges, then we're going to see it rise. However, in a tight system, a system that is ready to be charged, we will not see that number rise over 1,000 within 15 to 30 minutes. So that's called a decay test. So you pull the vacuum and then you shut everything off as if it's just a regular system, and you're watching the decay. You're watching the vacuum that you pulled decay over time. So if it is a dirty or wet system, that number is going to skyrocket up over 1,000, and you're going to need to do what's called a triple evac, which is when you pull again, you let it rise, and then you pull again and let it rise. And by the third time, usually it's gotten everything out of the system that it needs to get out. If it still has some in it, you need to go back and look and see if there's a leak, or if potentially, something really, really bad is stuck in there, some pieces of metal, something like that. But typically by the third time, it will be ready to go. After we have done that, we are going to unhook our vacuum pump, go back to our gauges, and we're going to charge. So we're going to hook our hoses then directly to the system on one side, and then on the back of these, they have another end of the hose, you guys. So you can hook one side to your manifold and one side to the system or whatever. So you're going to then hook to your refrigerant cylinder for 410A. They're pink. You're going to take that, flip it upside down on top of your refrigerant scale, hook to the unit, and then you're going to add charge. You're going to weigh it in. So again, we use PSI or poundage for systems like what I've shown you here today. And as we go through that and as we start putting it into the system, the scale itself will tell us how much we've put in. And there are lots of ways to tell how much the refrigerant needs. You can dial it in with your gauges, or you can read the design and then add for the line set. There's lots of ways to figure out how much refrigerant needs to be in a system, but that is from beginning to end the scope of work that you're doing if you are dealing with a refrigerant charge issue. Now, if it's just low on refrigerant and you gauged up and you didn't have a leak, it was already low and you don't need to do a leak check or fix anything, then it's just going to be simply add refrigerant to it until it is a proper subcool and superheat or vapor saturation, liquid saturation. If it is an overcharge, you're simply going to pull refrigerant out until it's at the proper charge. Again, lots of reasons that we would need to mess with the refrigerant charge, but most of the time, we don't need to at all. Most of the time, there's a broken wire, there's an overamping fan, there's a dirty coil. Some coils split into two, and they sit literally like this. So we see this side and we see this side, and it looks like it's one coil, but really in here is where the dirt's at. Make sure that you're inspecting your coils really, really well if you're going for maintenance. You guys, maintenance should always be for HVAC units, changing filters, checking coils, cleaning them if they're dirty, checking for wiring messes is what we call them. So if there's a rat's nest in there and you can't tell what wire is what, that gives a whole lot of potential for broken wires or for something to arc and short something out. So if you're going for maintenance and you open up the electrical compartment and you see all these wires everywhere, take that time to put a zip tie on them or a little piece of tape, whatever, make them orderly and neat and make sure they're not touching the metal sides or each other. That is one big thing you can do on maintenance that helps a lot with your HVAC units that you're taking care of. And then the other thing is airflow before charge. Always remember that even if you don't have your EPA license, a lot of the time you can still tell what's wrong with the system and properly diagnose it using temperatures, using visual inspections, smells, and sounds. If you hear, if it won't go into heating and you hear this loud chattering when it's trying to, you can, come from that it's probably the reversing valve. If every time it starts, it's making a really gross grinding sound, you can tell that the compressor's bad. If you smell something really, really, really bad, and you see oil on the ground, then the compressors experience burnout. There are so many ways as maintenance techs without EPAs that you can still work on and diagnose these systems. You just can't cut into the refrigeration cycle part of it. And that's why I wanted to show you guys today what the refrigeration cycle is, what is going on inside that system, and what we're doing to move, heat from one space to another and get rid of it outside. So yeah, that's a lot. I know it's a lot. It's a lot of me talking. I hope that you guys took, something worthy from this. If you guys would like to learn more, please download the SkillCat app from your app store, or you can reach out to me at HVAChicks Jennifer across all social media.